Hey guys, so I decided to do another video, a continuation of our review session from the other day. So I decided to do more problems using properties of matrices and determinants, more proof type of problems. But also I will dwell on something more on finding the inverse of matrices using the adjugate of a matrix. So let me start doing some of the problems. You will see that this will be very, some of the problems that are already have been given at previous exams, so I want to do some of those. Okay, so let me, all right, but first, before I even start and talking about those kind of problems, I want to talk to you about the adjugate of a matrix. More likely, I would like to dwell on the properties of the adjugate of a matrix. Sometimes this is called the adjoint of a matrix, but I would call it the adjugate. So let me recall you that, recall that the cofactor, and we denoted this by Cij, is the square matrix of A. Of the square matrix of Cij of the square matrix of A is -1 to the power I plus j times the determinant Remember that minor Mij, that's exactly what I'm going to talk about. So it's the determinant of the matrix obtained by deleting the ith row and jth column. So that was the, that's what we call the minor. So in other words, the adjugate of A, so I'm going to write it, the adjugate of A. So this will be equal to the following matrix. So this will be, so I'm going to take the cofactors, Cij, and I'm going to place them in the following way, C11, and now I'm going to do it C12, I'm going to put them on the column, and I'm going all the way to C1n, then C21, C22, all the way to C2n. And I keep going, and this is Cn1, Cn2, Cn, nn. Okay, so this is the adjugate of the matrix. Just like I said, it will be formed from these cofactors. So let me just remind you the formula. Cij is nothing else than -1 to the power I plus j times this Mij, where this is Mij is the minor let's say, it's the minor of the matrix A, right? So remember that this minor is nothing else than just the determinant of the matrix obtained by deleting the ith row and j column. That's what we call the minor. Okay. Now let me give you a quick example, and I would like to go even a bit further in using these kind of properties, such as adjugate of a matrix, in solving even systems of linear equations. So this is what I'll be talking about, the so-called the Cramer rule. But before we go into that, let me just give you an example. So the example I have in mind is the following. Find the example is the following. Find the adjugate of the matrix. And the following matrix is this one. A is -1, 3, 2, 0, -2, 1, and 1, 0, and -2. So we want to find the adjugate of this matrix. So in order for us to find the adjugate of the matrix, of course, we need to find all these cofactors. And keep in mind, so if we take this element here, so we need to find all the cofactors. So let's say the cofactor of -1. So this is C11. It will be nothing else than just -1 to the power 1 plus 1, which is 2, times the determinant of the matrix obtained by deleting the first row and the first column in this case. So this will be nothing else than -2, 1, 0, and -2. And if you do the computations of this, it will give you 4. So if you do all this, and I'll leave it to you as an exercise, so exercise, for you to compute C12, C13, C21, C22, C23, C31, C32, and C33. So after we compute all this, right, we will get just like the way you, for example, let's compute C12. Let me give you another example. It's -1 to the power 1 plus 2 times this determinant, which is given by what? Well, I'm deleting the first row and the second column. So it will be 0, 1, 1, -2. And this is nothing else than negative, the determinant 0, 1, 1, -2. So this will be nothing else than just -0 minus 1, which will be 1 at the end of the day. Anyway, so you keep doing all this, you compute all those cofactors, and once you do this, you're going to transpose that matrix obtained. So once you transpose that matrix obtained, so computing the cofactors will give us the following, the following matrix of cofactors. So I'm just going to write the matrix of the cofactors. So this will look like, so after you do all these computations, but like I said, I don't want to lose too much time with this, you will get something like 4, 1, 2, and then you will get something like 6, 0, 3, 7, 1, 2. I hope I didn't make any mistakes. So that should be in the, all right. Okay, so this is the matrix of the cofactors, and the transpose of A of this matrix, of the above matrix, so of this matrix of cofactors, is the adjugate. So is the adjugate. Of A, which is given by adjugate of A is nothing else. So we're just going to transpose this matrix. So it will give us 4, 1, 2, 6, 0, 3, 7, 1, 2. And that's how we're going to compute the adjugate of a matrix. This is just one example. We can have plenty of other examples. Let me try another one. But before I go into that, let me remind you something. So I told you there is why is the adjugate of a matrix important? So there was this theorem which says the following. There is a formula for the inverse of the adjugate of a matrix. And you will see that this formula is very important. So a formula for the inverse of a matrix, Let me denote this formula. So basically, the formula says the following, that if A is an n by n invertible matrix, then we have the following formula. The inverse, A inverse of is nothing else than just 1 over the determinant of A times the adjugate of A. So I've done this, I've talked about this in one of the lectures, but not for too long. It was briefly discussed. And there is one thing, and I'm not going to go into the proof of this too much. It's in the book. It basically, you just take the matrix A, you write it just the way it is by you write each entry of the matrix A. You take the adjugate of A, you write with just like the way it is with the entries, but the entries of the adjugate, keep in mind that they'll be the cofactor matrices. And then you're just going to multiply, just like row column multiplication. And at some point in this, you'll get the following. So the following formula, which is very important, you'll get that 8 times the adjugate of A commutes with the adjugate. That's a funny thing. I told you that not all matrices commute, but in this case, A commutes with the adjugate of A. And moreover, it is equal with the determinant times the identity. That's a very important equality. Now, of course, once I have this, well, that's why do I obtain this? Let me just give you a very brief argument. So when you write A times the adjugate of A, or the adjugate of A times A, at some point, when you multiply, when you do this multiplication, you'll have something like this. So on the main diagonal, you'll have the determinant of A. That's the funny thing. You keep going. And then the rest will be 0. And of course, now this is nothing else than just when you take out the determinant as it's a scalar, right? It's nothing else than just determinant of A times the identity. Okay, so that's very, very important thing for you to know. Okay, now with this, so since we have this formula, and let me, well, I mentioned this in class, but I'll mention it again. Let me give you another example of how to find the inverse. So example, find the inverse of the following matrix. And this matrix is given by, so it's A equals to, let's say, -1, 3, 2, 0, -2, 1, and 1, 0, -2. Let me take this matrix. So keep in mind that we had the formula. The previous formula, it was something like this. It was, so the formula was that the inverse, A inverse, is nothing else than just 1 over the determinant of A times the adjugate of A. And now what we need to do here is just to compute the determinant of the matrix, and of course we need to compute the adjugate of a matrix as well. So there's going to be a lot of work. So just like I've done previously, I'm just going to compute. In fact, let's say the determinant of a matrix, and I'll leave it to you as an exercise. Determinant of A will be it will be 3, and I'll leave it to you as an exercise. Why is 3? You have plenty of options here. You can use Cezar's rule if you want. You can expand on the first column. You see you have a 0 there, or you can expand on the third row. You have a 0 as well. But I think the first column would be better because you have a 0 and then you have a -1. And then the minors are very, very easy, very fast. Yeah, they can be computed very fast. All right, so the determinant is 3. This 3 is not 0. So this implies that A is invertible. Okay, and now we can compute the inverse. So the inverse, keep in mind, is using this formula above, is nothing else than 1/3 times the adjugate of A. In our case, the adjugate, once you do all this computation, I'm just gonna leave it to you as an exercise. It will be nothing else than just, I think, 4. Wait, let me look. Yeah, it's just the same matrix. It's 4, 6, 7. Yes, it's the same matrix. So 4, 6, 7, 1, 0, 1, and 2, 3, 2. And then you can plug this inside. So you'll get, since this is a scalar and we're multiplying by a matrix, we'll get 4/3, 2, 7/3, 1/3, 0, 1/3, 2/3, 1, and 2/3. Okay, so that's the inverse of the matrix. So that's the way you're gonna compute the inverse of a matrix using the adjugate. So keep in mind, once again, the procedure is that you compute the determinant. First of all, we know that the matrix is invertible if and only if the determinant is non-zero, so you have to compute that. So once you know that the determinant is not 0, then you can go further and you can compute the adjugate of A. So you can compute the cofactor matrix, and then at some point you'll get, you transpose the cofactor, the matrix of the cofactors, and then you'll get the formula. Okay, I think this, also I mentioned at some point that, well, I didn't do it in my lectures, unfortunately, but I want to do it now, is there is this rule which is very important, and in fact the proof will use this formula with the inverse and the adjugate, is what we call Cramer's rule. So Cramer's rule, it's, let me say a few words about it. So Cramer's rule, it's another way of solving systems of linear equations, using determinants. So this time we will use determinants to solve a system of linear equations. All right, so let me just give you a, well, I was thinking maybe I should give it the general rule, and then we'll see some examples. So Cramer's rule says the following. So let me state this as a theorem. Cramer's rule. All right. So it says the following: if a system of n linear equations in n variables has the coefficient matrix, A, okay, with a non-zero determinant, and this is very important information, determinant, I may denote this by a double bar, or you can denote it by the determinant of A. Then the solution of the system is given by the following. So x1 will be nothing else than determinant A1 over determinant of A. Then x2 will be nothing else than the determinant of A2 over the determinant of A. And we keep going all the way to xn will be nothing else than just the determinant of an over the determinant of A. Okay. Where, and this is very important to specify this, where the ith column of AI is the column column of constants in the system of equations. Okay, we'll see. So this is the formula. It's very simple, very direct. Anyway, I'm not going to dwell too much on the proof of this. The proof uses the adjugate of a matrix. So basically, you just represent this system AX equals B. In fact, let me say it just very quickly. So AX equals B. So that's the system of linear equations. And then you know that this system can, the solution for this can be represented. So the solution is given by x equals A inverse times B. So that's the solution of the system. But now the trick is that we can represent this inverse using the formula. So this guy here is nothing else than just 1 over the determinant of A times the adjugate of A, right? And now multiplying by the matrix B, it will give you something. It will give you this thing here. Once you do this, it will give you something like this vector column, vector transpose, right? And this, after you compute all this and you set them equal to, you'll get that this is nothing else than just the formulas that we have expressed for x. xi, for example, x1 will be nothing else than just 1 over the determinant of A times, and this will be B1 times C1i plus B2 times C2i, and we keep going. Bn is nothing else than Cni, right? And these Bi's are the entries, so where B1, Bn are the entries of B. Okay, so we have this. So that's how you're going to use the Cramer's rule. And now let me give you an example. So let me give you the a system which will look something like this. So solve, so exercise, solve the following system of linear equations. And I'm going to take a 3 by 3 equations, 3 variables. So I'm going to do this s by negative x plus 2y minus 3z equals 1 2x plus z equals 0. Anyway, it's a simple one. And 3x minus 4y plus 4z equals 2. Anyway, probably as you have been used by now, and by the way, I'm gonna, you have to make sure that you know how to solve systems of linear equations. I'm pretty sure you're gonna have one of these questions in your midterm and even final. Okay. But now I'm gonna leave it to you as an exercise to solving using the methods that we have talked about before. And now I'm just gonna use Cramer's rule. So the first thing before I even apply Cramer's rule, let's look at the, you see, if you look here, right, at the formula, x1 is the determinant of a 1 over x determinant of a. So before I even go and start talking about all this, I need to make sure that the determinant of A is non-zero. So in other words, the matrix is, the determinant of the coefficient matrix is not 0. So the determinant of the coefficient matrix is, let's say, let's denote this by a matrix. Let's say it's A. Let's call it A. Is, so the determinant of this will be -1. So the determinant of -1, 2, -3, 2, 0, 1, 3, -4, and 4. And then I'll leave it to you as an exercise to show that this determinant is not 0. In fact, this is equal to, if I look at it, probably 10. So we'll leave it to you as an exercise to prove this, that this is actually 10. And now, once I know this, the only thing I need to do is to apply Cramer's rule. So the way we're going to do it will be like this. So let's find the x. So we said that x will be nothing else, 1 over the determinant of A. So it will be 1 over 10 times the determinant of the matrix. And keep in mind what we said here. Let's go back. You see, where the column I is the column of constants in the systems of equations. So in other words, this will be 1 over 10 times the determinant of, it will be again a 3 by 3. And the first one, let me write this column, will be 1, 0, 2, right? Then I'll have 2, 0, -4, and then -3, 1, and 4. So what did I do? If you look closely, the only thing I did was just to replace the first column with the column of the free coefficients here, as you can see it, for x. Then for y, you're going to do the same thing. And then for z, you're going to do the same thing. So that's how you're going to do. You're going to replace the column. For example, when you have the columns of y, you'll replace the second column with the column of the free coefficient. So once we can start computing this again, this is just going to be a determinant. We can expand over, so after we expand, this will be 1 over 10 times, and let's expand over the, you see, we can expand over the second row here. I have 2 zeros. That's very convenient for me. So the first, I don't need to care about the first 2 minors or cofactors. They're just going to be gone. So it will be nothing else than, so this position will be 2/3. So it will be -1 to the power 2 plus 3, which is 5 times the matrix 1, 2, 2, -4, the determinant of this, which will give us, this will be 1 over 10 times -1 times this determinant, 1, 2, 2, negative 4. And after we do all these computations, this will be, okay, 4 over 5. And I will leave it to you as an exercise. So find y and z. Exercise. So to find y and z, we're going to do exactly the same thing, just like I mentioned. So that's the method of, this is how you solve systems of linear equations by just by using Cramer's rule. Okay. Now I want to do some other problems. I think I send you some of the, I send you the material, but I want to do it. So keep in mind that I told you at some point that about this relation for 2 by 2 matrices. So let me call this as a problem. So this is problem 1 in the notes that I send you. And I told you, in fact, to do the proof on your own, but anyway, I'm going to do it. So it's called the Cayley-Hamilton Equality. And this holds true for 2 by 2 matrices. This is very important in this form. So it says that show that for a 2 by 2 matrix, so in M2 of C, we have the following. We have that a squared minus trace of a times a plus the determinant of a times the identity is the null matrix. This is a very, very important. And in the first review session, I think I gave you a way of, I proved one of the problems that was given on some of my previous exams by just using the Cayley-Hamilton relation, right? It followed immediately, you know, basically. So now let's prove it. And I told you this also, I would like to mention one thing, and I think I've mentioned this, and I'm just going to keep saying it. This will be very important when we will talk about the, you will see that when we will talk about eigenvalues and eigenvectors, this Cayley-Hamilton relation will be will have a disguised, basically the same version of this relation, but in terms of the characteristic polynomial. Anyway, we'll go there and you'll see that this is nothing else than just this relation that we're about to prove here. All right, so I think I told you this, that the only way, direct way of how you can do this is just by doing the computations. So let's do it. So let's write, so consider this matrix, let A be, we can denote this matrix A with the entries A, B, and C, D, with A, B, C, D being complex numbers. And now we're going to compute everything. Keep in mind that the trace of A and the determinants are both scalars. So the trace of A is nothing else than the sum of the elements on the main diagonal of the matrix, and the determinant, it's a scalar, is nothing else than just AD minus BC. So these are the two scalars that we need to take into account. So now let's compute this. So we have A squared. It will be nothing else than just AB CD times AB CD. Okay, so we have this. So let's multiply this. So it will be A squared plus BC, AB plus BD. As you can see here, if I factor, I have the trace there. That's very interesting. AC plus DC. Again, if I factor C here, you'll see that it's C times A plus D. Again, the trace appears there as well. And the last one is BC plus D squared. Okay, so that's the A squared. Okay, now what are we going to do is just compute it. So let's do it. So let's see who is trace of A times A. So the trace of A, I told you, is just a scalar. So it's A plus D times this matrix A, B, C, D. And now if you multiply this, so it will be A plus D times A plus D times B, and A plus D times C and A plus D times D. Okay, so that's my matrix trace of A. And of course, you can multiply these elements inside it. It doesn't really matter. Okay, so you have this. Now, the only thing that's left for us is to see who is the determinant of A times the identity. So the determinant of A is AD minus BC. Again, it's a scalar, and the identity matrix is nothing else than 1 is 0, 0, 1. Keep in mind that this is how the identity matrix looks like. All right, so let's multiply this. So if we multiply, this will be AD minus BC, 0, 0, and AD minus BC. And now we're going to do all these computations. Okay, let's do this. Whew. So it will be, therefore, we have A squared minus trace of A times A plus the determinant of A times the identity is nothing else than just, okay, so now let's see what this matrix is. So, oh my. So this will be A squared plus BC, AB plus BD, and AC plus DC, BC plus D squared, okay, minus the second matrix was given by let's A squared plus AD, let's multiply these out, AB plus BD, AC plus DC, and the last one is AD plus D squared, okay, minus this plus this matrix, the determinant of A times the identity, which was nothing else than just AD minus BC, 0, 0, AD minus BC. Okay, now let's look. Keep in mind we have a negative here. This is very important, don't forget about it. This is a negative here. And now, let's see, let's look at the matrix. If we look closely, we have, you see, A squared. Okay, let's write it. So the first entry will be A squared plus BC minus A squared minus AD plus AD minus BC. Guess what? Look what happened here. So in other words, it will give us you 0. Okay, let me just erase this. And then I can put 0 here. And then you can figure it out yourselves that for the rest it will be 0 as well. So this will be nothing else than just the null matrix. That's a very, very important relation. I'm going to do some applications of this. Well, with all details and computations can be found in the notes, the review session notes that I have already sent you. So let me give you an application. So problem 2. So like I said, these kind of problems require a little bit of thinking. They're not super standard problems. So like I said, for those of you who want to get an A in this class, you need to solve one of these kind of problems. So one of them will be something very similar will be given at the midterm and also the final. All right, problem 2. Problem 2 says the following: show that if a matrix A is a 2 by 2 matrix with complex entries such that, let's say, A cubed equals the null matrix, then guess what happens? A squared will be the null matrix. Wow, this is quite a statement if you look at it, right? Because you'll be tempted to say, okay, I understand if A squared will be 0 and then I'm multiplying by 8, then I have no problem. A cubed will be 0, but the other way around, this really happens? Well, it looks like it does in this case. Right? Clearly, so once again, if a squared is 0, then a cubed is 0, right? Because a cubed is nothing else than just a squared times a. So if this guy is 0, then this will give you 0 times a, which will be 0. Then a cubed is 0. But we're not asked to prove that. Well, that is trivial, as you can see. We're not asked to prove this. We're asked to prove the converse of this. So if a cubed is 0, then a squared is 0. Wow. So how are we going to do this? Well, like I said, this problem requires a little bit of thinking. So it's not like super standard. So how are we going to approach this? Well, let's look. Let's analyze this, what we have. So we have that I have a matrix A such that a cubed equals O2, the null matrix. So let's write this. Let's write this down. So a cubed equals the null matrix. One thing to do here is just to take the determinant. So by taking the determinant, so applying the determinant, we have that the determinant of a cubed is nothing else than the determinant of O2. But the determinant of the null matrix is 0. That's obvious to see. But also the determinant of a cubed is nothing else, since this is the determinant of a times a times a. And using the property that the determinant is multiplicative, so here the determinant is multiplicative, we have that this is nothing else than the determinant of a times the determinant of a times the determinant of a, which is nothing else than the determinant of a cubed, everything cubed. So in other words, I know that the determinant of a cubed is nothing else than 0. So this implies that, so this is 0, we know that. So this implies that the determinant of a is actually 0. So the matrix is singular. So my matrix A is singular. Well, now let me apply the Cayley-Hamilton. So by the Cayley-Hamilton, so problem 1, by the Cayley-Hamilton, so by the Cayley-Hamilton, well, I forgot that anyway, my mic was turned off, but anyway, now I turn it on. So by the Cayley-Hamilton relation, we have the following. We have that a squared minus trace of a times a plus the determinant of a times the identity is 0, right? So this is problem 1. But now we know that the determinant of a is 0, right? So the determinant of a is 0, and now this implies that a squared is nothing else than just trace of a times a, right? Okay. Now, since a squared is trace of a times a, well, no problem. Let me multiply by an a to the left, to the right, it doesn't really matter. And we'll get that a squared times a is nothing else than trace of a times a, which will be equal to trace of a times a squared. So this will be equivalent with a cubed equals trace of a times a squared. But if I look here above, I know that a squared is trace of a times a. So this will be equal to trace of a times trace of a times a.
which will be trace of A. And let's put this squared times the matrix A. And I know that this guy, A cubed, is 0, is the null matrix. So now I have the following. So we have that trace of A squared times A is the null matrix, right? So this is the null matrix. And I have two options here. Either the scalar is 0, so if trace of A squared is 0, then trace of A is 0. But if trace of A is 0, from this fact here, let's call this star, since I know that A squared is trace of A times A, this will imply that A squared is 0. So, which is exactly what we wanted to prove. Okay. If now, so the other option, if A is the null matrix, then obviously, A squared is A or A times A, which is again, and this is the null matrix, and we're done. So in both cases, either case, we're done. Okay, and that is the problem. There are some other problems. I've done a few problems using the inverse of the matrix, and we've done something about the LU factorization. So I will avoid that. Let me do some other problems. For example, another problem I wanted to do is the following, which is problem number 8 from the notes. And it says the following. In fact, all these problems, I take them from the book. They're like those problems in the book that they write proof. So let's say the more difficult problems from the book. These are the problems. And problem number 8 says the following. A square matrix is skew symmetric when A transpose is equal to negative A. Prove that if an n by n, if A is an, okay, let me write it like this. If A is an n by n symmetric, skew symmetric matrix, then we have the following formula for the determinant. The determinant of A is nothing else than just -1 to the power n times the determinant of A. Well, let's look at this problem for a bit. Let's analyze it together. So we know that we have this equality. A transpose is nothing else than negative A. So just like we did previously, a good idea is to take the determinant. So apply the determinant here. So this will imply that the determinant of A transpose equals the determinant of negative A, right? So once we apply the determinant, we get this. But we know that the determinant of A transpose by the properties of the determinants is nothing else than just the determinant of A. So we have that the determinant of A is nothing else than just the determinant of negative A. But the determinant of negative A will be nothing else than just -1 to the power n times the determinant of A. And therefore, we get exactly what we wanted to prove, which is here. That's it. That's a problem. wasn't a big deal. You just had to take the determinant. So it was very, like I said, are 1 or 2 liners, but they require some idea. Okay, another problem is I want to do these problems because it's about the trace and the determinant of a matrix, and I would like to do them. They're very important. So problem 9 says the following. So it says that find 2 matrices, find two by 2 matrices such that the determinant of A plus B is equal to the determinant of A plus the determinant of B. We said in class something, and that's very important. We said that the determinant is not additive in general. It's only multiplicative. And we said about the trace that it's not multiplicative, it's only additive. All right? So for here, this implies that this will not hold true for all 2 by 2 or n by n matrices, but for some matrices, it will hold true. And now I'm asked to find some examples of 2 by 2 matrices for which I have the determinant of A plus B, for which the determinant function is additive. So in other words, for which determinant of A plus B equals the determinant of A plus the determinant of B. Well, let's think of some matrices. Just like I told you, this property doesn't hold true in general. So let's cook up some matrices. So consider the matrices. Let's say A to be equal to, let's say, -1, 0, and 0, 1. And B to be, let's take the identity. I'll take the simplest examples possible. And now, once I put my hands on these 2 matrices, now I'm good to go for and do the computation. So first of all, let's see who is A plus B. So A plus B is nothing else than just -1, 0, 0, 1 plus the identity matrix. So this will be, if you add them, add these 2 matrices, this will give us 0, 0, 0, and 2. So the determinant of the A plus B of this matrix is nothing else than just 0. It's 0 times 2 minus 0 times 0, which is 0. So this matrix is actually singular. So it's, but now let's compute the determinant of each one of them. So the determinant of A is what? Is -1, right? -1 times 1 minus 0 times 0. So this will be -1. And the determinant of B is 1. It's nothing else than just the determinant of the identity. Now it's quite clear that 0 is in fact -1 plus 1. And this could be translated into determinant of A plus B is nothing else than just determinant of A plus the determinant of B. And therefore, we found an example of 2 by 2 matrices for which the determinant is additive. So determinant of A plus B equals the determinant of A plus the determinant of B. All right. Now let me address the same problem for the trace. But this time I'm going to ask you something. I'm going to phrase the question a bit different. So the problem is the following. So it's problem 10 from the notes, which says the following. Let A and B be n by n matrices. And I want you to be very careful here when I phrase this. And the question is it always true that trace of A, B equals trace of A times trace of B. So in other words, the trace is multiplicative, question mark. If it is true, prove it. If not, give a counterexample. So you see the phrasing, it's I could have asked the same thing for the previous question. So the phrasing is the following. When I'm asking you to prove something, so we understand the following. When I'm asking you to prove something, like, I don't know, prove that this happens, you have to prove it. But if I'm asking you, like, show that this doesn't hold true, it's enough for you to provide a counterexample for something that doesn't hold true. Look, I have you, you make this statement, and I feel this statement is not true, and I'm providing a counterexample for this statement. For example, in this case, it's like a question. So you have two options. You either you think it's true, then you have to prove it, or if you think it's not true, maybe you should give a counterexample. So, and I've said this numerous times in class. I already told you that the trace, and I'm gonna say it again, the trace of a matrix is not multiplicative. Very important. It's only additive. So this holds true. Trace of A plus B equals trace of A plus trace of B, which is very easy to prove. So keep in mind that. Make sure you don't make this mistake. That's why I always want to give you these counterexamples. So now you'll be tempted to say that, okay, maybe I'm tempted to say that, actually, maybe this is not true. Well, if it's not true, maybe I should put my hands on a counterexample. And what I'm going to do is the following. Since this is for n by n, let me just give you let me take the simplest one. Take n equals 2. Let's see for 2 by 2. It's enough for me to look at 2 by 2. So I only need to provide a counterexample to find two matrices A and B. Doesn't matter, 2 by 2, 3 by 3, 4, so that that property doesn't hold true, and then I'm done. So, for example, let's take 2 by 2, and let me take these matrices. I'm going to consider something similar to the previous example, but maybe something I will tweak it a bit. So I'm going to break the identity into two matrices that will look like this: 1, 0, 0, 0. So let me take this matrix first. Of course, I'm going to consider singular matrices. I don't need to bother myself with, because I'm not interested in the determinant here. I'm only interested in the trace. And B should be something like, okay, I'm going to take 0, 0, 0, 1. So I'm going to just, all right. So clearly trace of A is 1, right? Trace of B is 1 again. And let's look who is A plus B. AB. So let's multiply these two matrices. So AB is 1, 0, 0, 0, 0, 0, 0, 1. So this will be equal to, ouch. So once you do the computations, this will give you 0, 0, this is the null matrix. And clearly trace of AB is trace of the null matrix, which is 0. Well, as you can see, trace of AB is not equal to trace of A. So therefore, trace of AB, which is 0, is not trace of A plus times trace of B, which is 1 times 1, which is 1. And we're done. So that's the way to prove this problem. Okay, I think I'm gonna do one more example, and probably I'm gonna stop after this. there are some other questions, or maybe let me do 2 more examples. So the first example that I have in mind is the following, and I'm going to take a problem given at the, okay, stay with me on this one. Problem 11 from the notes. This was given at the Harvard University linear algebra exam. I don't recall which year, but probably it's a recent one. I think somebody showed it to me, and then I was like, okay, that's a nice problem. Maybe I should give it to my students. Anyway, so the problem says the following: a 2 by 2 matrix A satisfies trace of A squared equals 5 and trace of A equals 3. And we're asked to find the determinant. Find the determinant of A. B, a 2 by 2 matrix A has 2 parallel columns, and we need to interpret this. 2 parallel columns, and trace of A is 5. Find trace of A squared. Well, it's easy to look at this problem once you know about the eigenvalues of the matrix. It's quite trivial, but we don't know that yet. So this was given at the Harvard University final exam. So probably the method they used, I don't know the exact solution that they gave for this problem, but I will assume that it was solved using eigenvalues and eigenvectors. But like I said, we don't know that yet. So the only option we have here, it's maybe we could use something like Cayley-Hamilton or just computation. So let's do this. So let's look at part A. Let's analyze it a bit. So we have a 2 by 2 matrix that satisfies the trace of A squared is 5 and the trace of A is 3, and we need to find the determinant. Okay. So in other words, since I'm, if I see here something about the A squared, so I need to compute the A squared. So A squared will be A times A. It will be A, B, C, D. So let's do the computations again. A, B, C, D. And once we multiply all this, this will be give us A squared plus B, C, A, B plus B, D. A, C plus CD and BC plus D squared. Okay, I hope I didn't do any mistake. Okay, and now I know that trace of A squared is 5, right? Trace of A squared is 5, and we know that, and trace of A is 3. Sorry. Okay. So what does this mean? So let's take the trace. So the trace of A squared. So we have that 5 equals the trace of A squared, which is not just by adding the elements on the main diagonal. This will be A squared plus BC plus BC plus D squared, which is nothing else than, let's write this. So A squared plus 2BC plus D squared. And this is 5. And also we know that the trace of A, which is 3, is A plus D. So we have this. And we need to find the determinant. So let's write it again. So we'll have, okay, let's write this as like a system. We have that A squared plus 2BC plus D squared equals 5, and that A plus D equals 3. And what we need to find from here is the determinant of A. So the determinant of A was nothing else than AD minus BC. So we need to find this. So how to do it? So let's do something. So the determinant of A is AD minus BC. So that's the definition. And now I have to write it in terms of that A squared plus D squared. And I also have BC there. So we can do the following trick. It's a computational trick. It's 1/2 times A plus D squared, because here I know what this is, minus A squared plus 2BC plus D squared, right? So this is nothing else than just 1/2 times 3 squared minus 5. And this will be 2. That was a trick. It was a bit tricky though, because you need to see this writing here. So, okay, let me give you a reasoning why this is true. This identity is true here. So why? Well, if you look closely, if you look at the A plus D squared, this is nothing else than just A squared plus D squared plus 2AD. So the A squares, and it will stay only AD minus BC with 2 times in front of it, times 1/2, it will be exactly the determinant. So that's the trick. There's nothing special to see. All right. Now let's do part B. So part B says the following, and pay attention, this is a bit tricky. 2x2 matrix A has 2 parallel columns, and the trace of A is 5. So I need to find the trace of A squared. So if I have so since 2 columns are parallel, then we can write A as, I guess we're going to write it like this. So it's A, R times A, C, R times C, where this R is just a number, complex number. And then we know that a trace of A, which is 5 in this case, is equal to the sum of the main diagonal. So it's A plus RC. And now we want to use, so I want to use the formula. So keep in mind, I want to, so I want to use the formula for the trace of A squared from part A, right? So keep in mind that the formula for trace of A squared is, so in our case, it will be, so we know that trace of A squared is A squared plus 2 times RA plus RC squared, which is nothing else than A plus RC, everything squared, which is 5 squared, which is 25. So that's it. So we're using part A, we derived the formula for trace of A squared. So that was a problem given at the Harvard University final exam, probably. Probably I'll get back to this problem and you will see a more direct way of how to solve it using eigenvalues. It's like 1 or 2 lines, but even with this method, it's not hard at all. It's not complicated at all. Another problem that I have in mind, and probably I'm going to stop here, will be the following. Okay, so it's problem 13. Let A and B be 2 by 2 matrices such that AB, everything squared, is the null matrix. Show that B times A and everything squared is the null matrix. Okay. You see, this is very nice. If AB squared is the null matrix, then BA everything squared is the null matrix. Well, like I say, since there are 2 by 2 matrices, of course, you can assume that they have complex entries, real entries. It doesn't really matter that much. Well, we have to look for something that is valid for all 2 by 2 matrices, and that's something, and we said this, is nothing else than Cayley-Hamilton. So remember the Cayley-Hamilton equality. Right? Okay. And now we're trying to use this, and this time I'm going to use it for both, for AB, because I have some information about AB squared, but also I want to use it for BA as well. We see what we're going to get. So let's take X to be AB. So we're going to get what? So by Cayley-Hamilton, so in Cayley-Hamilton equality. Okay, so if we do this, we're going to have the following. So we're going to have AB squared, AB everything squared, minus trace of AB times AB plus the determinant of AB times the identity is the null matrix. Okay, now I'm going to do the same thing for this time for X equals BA. In again, the Cayley-Hamilton equality. And we're going to have that BA squared, BA everything squared, minus trace of BA times BA plus the determinant of BA times the identity is the null matrix. Okay, so we have these two identities. So let me denote this by 1 and this is by 2. So we have to kind of put them together to see how this would look like. Okay. So let's see. So we know that this guy is the 0. And also we have to prove that this guy is 0. Okay. Ouch. BA is 0. Okay. So we know this. So this implies, and we also know that the determinant is multiplicative. So the determinant of AB is nothing else than just the determinant of BA. So let's take the first one. So this will be that will be that trace of AB times AB equals the determinant of AB times the identity. Okay, okay, but I also know something. Since AB squared equals 0, since, so the relation from 1, we have this, since AB squared equals 0 is the null matrix, we can take the determinant. By applying the determinant, we have the following. we have that the determinant of AB squared is 0, but this will be equivalent with the determinant of AB everything squared is 0 by the properties of the determinant, and this will give us that the determinant of AB is 0. Okay, so this guy will be 0 here. So this implies that trace of AB times trace of AB times AB equals the null matrix is 0. So we have this relation. Okay, so from here we need to do something. So let's look at this equality 2. So let's look again at equality 2. So it's BA squared minus trace of BA times BA plus the determinant of BA equals times the identity equals the null matrix. Well, we've seen the fact that the determinant of AB equals 0. So this will imply that since the determinant is multiplicative is also the determinant of BA equals 0. So this guy will vanish here. Okay. So this will be equivalent with BA squared is trace of BA times BA. Okay, so we have this and we know this here. And what do we have in this identity here? We have that, let's call this 3. And in the identity 3, we have that the scalar, keep in mind that the scalar with the trace is a scalar. So we have that the trace of AB. So basically, a scalar times a matrix is the null matrix. So we have two options: either the scalar is 0, either the matrix is 0. So let's say we have case 1. Let's say case 1. If trace of AB is 0, we know from the properties of traces that trace of AB equals the trace of BA. So let me write it here. Trace of AB is the trace of BA. And this will imply that the trace of BA equals 0. Well, if the trace of BA equals 0, this implies that BA squared is nothing else than just 0 times BA, which will give you the null matrix when we're done. Case 2, if instead of the scalar to be 0, we have if AB equals 0. Then we have to show that BA is 0. So if AB is 0, then BA squared is 0. So how to do it from here? So we have that BA squared is BA times BA. And we know that well, in my notes, now that I look at my notes, I've done it a bit different, but anyway, it doesn't matter. Both methods are okay. So we can use the associativity of the matrix. So we'll have B times AB times A. So this guy is 0 here. And this is nothing else than B times 0 times A. And this will give you 0. That's it. In both cases, it will follow that BA squared is 0, and that's the end of the problem. All right, guys, so there are plenty of other examples in my notes. I'll send you the notes later on today, tonight. And also, I'll post this video on YouTube. Thank you very much. Let me stop the recording.